Hey, welcome back. Woo! It's been a tough. That first one was tough, I know. All right, but keep with it, rewatch it, and ask me questions. That's the important part here, guys. Okay, keep with it. Ask me questions. So let's take a look at this next example. Let's see if this helps us out any. He says here, find a function with y equals f of x with this derivative right here. And it satisfies the condition y f of 3 is equal to 5. All right, so we just got done talking about some stuff where if I make a function and say y equals f of x is equal to the integral from some number a, I don't know, we're going to pick that out later, 2x of tangent of u du, that when I take the derivative dy dx, well, dy dx for this particular one is equal to tangent of x. And that's what we just found out. And now if you look at that, hey, that looks really, really close to what I want, right? I want the derivative to be tangent of x. So I got that part down. Now I need to go to the next part, which says f of 3 has got to equal 5. Well, okay, so what would f of 3 look like to start with? So f of 3 would look like the integral from a to 3 of tangent u du. Okay, and I want to somehow make that equal to 5. I want all of that to equal 5. And this is where we're going to be a little sneaky. Okay? Here's the sneaky part. We can choose a to be anything, right? Because it didn't matter what a was. A could be 6, 10, 52, 5,000. And when I take the derivative, it will always be that tangent of x. So let's be a little sneaky. I know that there's a rule that says what happens if I let a be equal to 3? That means that instead of a being a, now I cross this out and I get a is equal to 3. And now when I go ahead and I do the integral from 3 to 3, we find ourselves, oh gosh, well that's going to be 0. But I want f of 3 not to be 0, because the integral from 3 to 3 is 0. There's no area under there, right? Okay, well, how can I get it to be 5? I want it to be 5, but I'm stuck at 0. I'm going to add 5. And now it equals 5. Say, what? Yes, you can do that. Okay? So what does that mean my final answer is going to be? It's going to look like this. It's going to be my y is equal to f of x, which is equal to the integral from 3 to x tangent u du plus 5. And why does this work? Because I found out when my derivative of this business here is tangent of x, and the derivative of 5, what's the derivative of 5? 0. Oh, and the derivative comes out what I want. That's even 10 times better. Isn't that amazing? And it's just a little trick, a little algebra. And this is where everyone loves algebra. All right? So let's go what's next. So next we get to our second fundamental theorem. So next we get to our second fundamental theorem of calculus. And what does it do for us? Well, it gives us this information up here. And it's saying, well, since I found my first fundamental said if I take the derivative of an integral, I'm going to just get my original function. The integral part of it is an antiderivative of f. We already know that. Therefore, if f is the capital F is any antiderivative of f, means it's kind of generic, okay, then this integral part I can say is any function f of x, or the antiderivative of x plus c, where c is any constant. Oh, that's getting heavy. It's super heavy. Okay. Well, what is this saying? Okay. Well, if you take back what we just looked at, right, that last example, it didn't matter what I put in there as a plus c, right? Okay, because what happens if I put any number in there and I take the derivative of it, it goes to 0, it goes away. So it doesn't matter what we can add to it. I can add anything I want to it. Okay, so now we're going to do a little bit of manipulation here so I can derive, if you will, the second fundamental theorem of calculus. Okay, and so what they will ask me to do here is rewrite the integral equation substituting x is equal to a. So I do that. I'm going to take this piece right here and substitute a. So integral from a to a, f of t dt. But we already figured that out, and if that's going to equal capital F of a plus some c. So explain the geometric meaning of the definite integral and its value. Well, number 2 says, okay, so definite integral. So I'm going it's my area from a to a. So there's 0 area. So the answer of my integral from a to a of f of t dt is equal to 0. Okay, which means that f of a plus c is equal to 0. And that means that what? C is equal to negative f, capital F of a, if you solve for c. So now if I go back and take a look at my original equation right here, okay, I can go ahead and substitute in c and say, well, if I just want to find out if I start with any a, okay, now my a means something now. How can I find out my area underneath the derivative part? My antit might be the capital F of x minus f of a. I just substituted in. So this allows us to evaluate the definite integral from any a, number a to number x. So what does this look graphically? Okay, so let me show you what this means graphically. Okay, and with the integral, this is going to take a little bit of time. Okay, since I know that if I say, for instance, if I'm going to make this claim real fast, 0a less than, I don't even need to do that part. I'm going to make that part just makes it easier. Okay, I make that claim, graphically speaking. Here it is. Here's A. Here's B. Boom. I want to find this area underneath here. Alright, so let's say I have this function, alright, that is described as f of x is equal to the integral from 0 to x f of t dt. Well, then how can I get this area here, okay, that's there, because that's what I want to find. Well, I can say, well, if I find out what f of b is, that's going to equal the from 0 to b of f of t dt. And I can find out what capital F of a is equal to the integral from 0 to a of f of t dt. And I do these in different colors. I say, well, f of this here is going to be all of this in green. And the f of a part is the area in blue. Okay. And what do I want? I want just this red area right in here. So what can I do? I can take the green and subtract out the blue. In other words, I want to be able to say my green, f of b, minus my blue, f of a is going to be equal to the area underneath this curve, which is the integral from a to b of f of t dt. Either one of these will work for you, okay? Hopefully this helps you understand it a little bit better. But how do we actually use it, okay? That's the important part, okay? So here it is again, just stated for you, okay? Here's kind of another way to say it. The integral evaluation theorem, or the fundamental theorem of calculus, part 2, means that we can evaluate a definite integral by computing the antiderivative of b minus the antiderivative of a, where f is any antiderivative, okay? So how does this actually work? So here's a problem, okay? My integral from negative 1 to 3 of x cubed plus 1 dx. So I want to find a function whose derivative is x cubed plus 1. Okay? So I want to find a function whose derivative is x cubed plus 1. So this is where you got to undo what you have done. So there's a little bit of thing, well, if it's x cubed, okay, well, I know it's going to be, if my derivative is x cubed, I know it's going to be x to the 4th to start with, because then I multiply, okay, and I lose 1, so it'll be x cubed. Good. Plus, I know, well, if it's 1, I know I'm going to have x. But the problem is the way that this is written right now, if I take the derivative, right, I get 4x cubed plus a 1. Well, I don't want the 4. I just want x cubed. Well, how do I do that? Well, I can just go ahead and divide, well, if this was divided by 4 to begin with, and now this is divided by 4 to begin with. Oh, okay, so now when I multiply by 4, the 4's cancel, I'm left with x cubed plus 1. So this is my antiderivative. Well, now I can use that theorem I just came with, the second part of the fundamental theorem of calculus, and use my antiderivative. Because remember that second part of the fundamental theorem of calculus said that the integral from negative 1 to 3 of x cubed plus 1 is equal to the antiderivative at 3 minus the antiderivative at negative 1. Oh, okay. Well, I can go ahead and just plug in, right? So that's what I'll do. I'll just go ahead and plug in. Well, capital F of 3, well, okay, that's going to be 81 over 4 plus 3 minus f of negative 1, 1/4 minus 1. Okay? And that's my answer, and I can consider that good enough. All right? Now, I'm going to tell you this. All right? So the proper way to do this, and if you, this is fine, doing it just like this. If you're able to go ahead and just evaluate, what you're going to be able to say is that you can say that the integral from negative 1 to 3 of x cubed plus 1, well, that's going to be equal to, well, my antiderivative, okay, evaluated from 3 to negative 1, and get your same answer and do the same thing right there. Okay, so there are two ways to go ahead and do this as far as that. If you want to, you know, this is the more compact way of doing it. This is using or showing the fundamental theorem of calculus. Either way, whichever one best suits you. All right, okay, let's take a look at what's next. So here's your homework, 21 to 39 on odd. I will tell you this, just keep asking yourself the same question when we get there, which is, okay, what function, when I take a derivative, gives me this? And by that I mean this here. Look at that function, look at that piece there, and ask yourself that question. What function, when I take a derivative, gives me this? Ask yourself that question every time, and you'll be fine. Okay? Come to me with questions. Have a great day.